I'm going to continue to explain zero knowledge through example. At this point, things are going to get more mathematical, and we're going to talk about a zero knowledge protocol for quadratic residuosity and then illustrate definitions through that. So for this, we need a little bit of math background. So we're going to go back to some of the algebra and just introduce a little bit of terminology. So we know what it means for a number to be a square root of another, or for some number to be a square. So 3 is a square root of 9, and that makes 9 a square. So that's over normal integers, but you can do the same thing in modular arithmetic. So suppose n is an integer, the modulus, then you have a number in the group Zn star. Well, it is a square root of another number in the group, if the obvious thing is true. If I square little x, I get back big X. But now that operation is modulo n, it's in the group. And again, quite obviously, we'll say that big X is a square if it has a square root. If there's some little x such that little x square mod n is big X. Just as with integers, not all numbers are squares. So 8, for example, has no integer square root. In modular arithmetic, some numbers are squares and some are not. Squares are also called quadratic residues. That's a more mathematical term. Having fixed this modulus, let's define a few sets. This is the set of all square roots of x relative to n. What that means is that look inside the group Zn star, to which big X belongs, and collect all the little x's which when squared give you back big X mod n. There could be no such little x's. That would happen if big X is a non-square. Or if x is a square, well, there may be many of them. And again, that's familiar from the integers where 9 has 2 square roots, 3 and -3. Since not all big X's are squares, we'll collect up into this set all the ones that are. We write that formally as saying the set of square roots is non-empty to put X in this set. We call it the set of quadratic residues. This is parameterized by the integer n because all this is modulo n. Here we collect up, and this we call the language of quadratic residues, all pairs n and x, where x is a square mod n. Okay, so we have these 3 sets. Let's play with the little examples to illustrate that. So we've often used in prior chapters the case where n is 11, because then Zn star is just the numbers 1 through 10, the fingers on our hand, and it's kind of fun to see that those very familiar numbers have some properties we may not have seen before. So what I did here is I wrote on all possible x's in Zn star, and I just squared all of them. Of course, squaring is mod 11. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 16 mod 11 is 5, 5 squared is 25, 25 mod 11 is 3. Now you notice that after this, things repeat backwards, and you would expect that. Why? Because 6 is the same as -5 mod 11. 7 is the same as -3 mod 11. Any two numbers which add up to 10 are negatives of each other. Or add up to 11, I mean, are negatives of each other. Okay, what can we glean from this table? The 5, look at the number 5. Well, is it a square? What tells you it's a square is that it appears in the second row. So it's here. What are its square roots? 4, but also 7, because both of them squared give you 5. What about the number 6? Well, it doesn't appear here at all. It's not a square, hence, and so the set of square roots of that is the empty set. What are the quadratic residues mod 11? They are whatever appears here. So that gives us 1, 3, 4, 5, 9. There's a bunch of facts about arithmetic on squares in Zn star, which are kind of intuitive and worth writing down since we'll use them. So this says that if we fix the modulus n and take some big X, we want to know whether it's a square or not. That happens if and only if its inverse is a square. So remember, in this group, every point has an inverse. So whether X is a square or not is equivalent to whether its inverse is a square or not. Also, similarly, if little x is a square root of big X, then the inverse of little x is a square root of the inverse of big X. Now again, these are kind of obvious if you think about normal arithmetic, and the facts are saying they transfer to modular. Okay, so I recall at the top these three sets. Now, while we could pursue all these zero-knowledge protocols at this point, just given those definitions, some of the things that make them interesting relate to the computational complexity of these problems. And so we'll just say a little bit about that. If you look at this language of quadratic residues, suppose I ask you to test membership in it. That means I give you a pair n and x, and I ask you, is it in the set of quadratic residues? Can you determine, in other words, whether big X is a square mod n? And it turns out there's no known fast algorithm to do that. There's no polynomial time algorithm we know of that's able to solve that problem on all instances. Why is this interesting here? Because now if Peggy makes a claim, look, I have a pair n comma x and it belongs to QR, Vic finds that claim interesting because he couldn't test on his own that it's true. He needs Peggy's help to determine it. Another problem you could consider is I give you a pair n and x, which I know now to be in QR. That means I know that big X is a square mod n, so it has square roots mod n. But I ask you to find them. Go find a square root. It turns out again that this is not easy. In general, for arbitrary n, we don't have such a algorithm, a fast algorithm to do this. Now, it turns out that some cases are easy. For example, if big N is a prime, you can easily find square roots or determine whether something is a square or not. And if you have the prime factorization of big N, you can also do these kinds of things. We can contrast them with another problem, which we'll also see arising. Suppose I give you just a modulus, and I just say, find me a square. I don't care what square it is, just give me a number that's a square. Well, there's many ways of doing that. Certainly one is I just say 1, because the number 1 is a square. But something a little more interesting is that I can pick a random point in Zn star and square it and give you that back. And by that method, I kind of generate squares with equal probability across the set of all squares. And that will be useful for us. So what is our goal here? It's to enable Peggy to prove quadratic residuosity. What that means is that these parties both have as input a pair n and x, modulus, and some big X and Zn star. And Peggy is claiming that this pair actually is in the language of quadratic residues, meaning big X is a square mod n. She has evidence for that. She actually has a square root. She knows a little x whose square mod n is big X. So the protocol now is supposed to convince Vic that big X is indeed a square mod n, but it doesn't want to reveal little x. So Vic, remember, outputs a Boolean decision. We say he accepts if the output's true. So as we discuss this, it's maybe worth clarifying what we mean by a protocol. So a protocol is the steps that we as designers ask the parties to execute. It's just an algorithm. Like when we had cryptographic schemes, we had algorithms for, let's say, encrypting a message and decrypting it. The protocols are the equivalent of those for Peggy and Vic here. But parties need not follow them. We call them honest if they execute the algorithm or protocol we prescribed, and cheating if they don't. In the setup we have here, the verifier is always honest, but whether the prover is honest or not depends on what condition we're interested in. So here are the properties we want from our protocol for quadratic residuosity. It's the same three we saw before, but now it's a little more precise. Completeness says that if the claim is true, that means the pair n, x really is in the language of quadratic residues, and if Peggy is honest, meaning she follows whatever steps we prescribed, we haven't yet set what those steps are, but we will in a bit, then the verifier must always accept. Soundness says now Peggy is an adversary. She has claimed that the pair n, x is in the language of quadratic residues, but it really isn't. In fact, big X has no square root. It's a non-square. So she, in the process of trying to convince Vic of that, is not going to follow the prescribed algorithm protocol. She's going to do whatever she wants. She's going to send flows that are arbitrary. Nonetheless, the verifier should not accept, except with some probability, say a half. That shows that the proof is convincing, which we call sound. When we consider zero knowledge, we return back to an honest Peggy. This is Peggy who says, I want to protect my secret information, so I will follow your prescribed algorithm, and I hope to convince the verifier without the verifier learning my secrets. So in this case, the claim n, x is true. The x is a square mod n. And Peggy has a little x that's the square root of big X, and she follows the protocol. And what we now want is the verifier does not learn what that secret little x is. That's the zero knowledge aspect. So those are just requirements. What we now have to think about is how are we going to make this happen so that we have all three of those conditions. So let's start with something naive. What Peggy does, remember she has little x whose square is big X. And what she's going to do is simply send that over to Vic. I will write it as this to change the name of it, but she sends him the X value. What he does is check that it really is the square root of big X, which is easy. He can just square this value mod n. That's a simple operation that takes linear time in the number of group operations. And if that yields big X, then he says yes, otherwise he says no. What properties does this protocol have? It's very good for completeness and soundness, but other properties are more challenging. So in particular, if n, x is a quadratic residue and Peggy follows the protocol, certainly Vic will accept, because here he gets the square root of big X and he squares it, and of course he gets back big X. But it's also has soundness. Now, this is a simple example where we can learn to think about soundness a little bit, so let's look at it a little more detail. What we're worried about here is that the prover has become malicious. She has put forth this claim that this is in the language of quadratic residues, but it isn't actually. So big X is not a square mod n. She's going to try to convince Vic nonetheless that it is. She knows what Vic does. He squares what he gets and checks if it equals big X. She's trying to find something to send here that would lead Vic to accepting. There is no restriction on what she puts here. You could say, well, does she put little x or not? But it doesn't even make sense. There is no little x anymore. But what we notice is no matter what she sends, if big X is a non-residue, there is no way the verifier will accept. Why is that? Because this big X simply doesn't have a square root. No matter how hard Peggy works, she cannot find any value here whose square is big X. Okay? And that's not a computational restriction, it's a mathematical one. There simply does not exist a square root for big X. So with probability 1, Vic will reject. And we had only required him to reject with probably at least a half, so this is even better than one we wanted. The difficulty, of course, is that there's no zero knowledge here. The thing we want to hide, the little x, has just been sent in the clear. So we need to get around that. Now, the way we're going to do that is to break the claim that big X is a square up into two subclaims via something we call splitting. So let's write big X as a product of two things. One we call commit, CMT, the other we call Y. So fine, we write it like that. Now, if we know that big X is a product of two things, it turns out there's some nice facts which enable us to reason about whether or not big X is a square. So what the first statement is, it says, suppose both this and this are squares. Both belong to the set of quadratic residues mod n. You're then guaranteed that big X is a square. Right? So somehow knowledge about the quadratic residuosity of these two things transfers over to big X. Just take the contrapositive of that statement. It says if big X is a non-square, then either this is a non-square or this is a non-square. Right? And that's just the logical contrapositive. How is this going to help us? We'll see that in a little bit. Maybe we can first just briefly discuss the justification of these claims. Informally, it's really trivial. All it's saying is, well, why is big X a square if both of these are? Well, because the square root of big X is just the product of the square roots of the other two things. So if this value exists and this value exists, then so does this value. You can also go through a more careful proof, which really reflects the definitions. So if you know that commit is a quadratic residue, then you can find a little c such that c squared mod n is this. Similarly, if we assume that big Y is a quadratic residue, we can write it as little y squared for some little y. Now take the product of these two square roots c and y, and notice that that's a square root of big X. Why? Clearly, if you square w, you get c squared y squared, which is this times this, and this times this we assumed was equal to big X. So now we know that w is a square root of big X, and that makes big X a quadratic residue. Okay, so we are now going to use this splitting capability for a zero-knowledge protocol. So the setup, remember again, is that both parties have the claim big N and X. Peggy is claiming that this pair is in the language of quadratic residues, and if her claim is true, she has a square root little x of big X, but she doesn't want to reveal it. And we're going to create a 3-move protocol. Unlike our prior protocol where there was only one interaction, now Peggy will send something called a commitment, Vic will send something back called a challenge, Peggy will send something called a response, and only then will Vic make a decision. So at a high level, what Peggy does is she splits up this big X as commit times Y for some values that she's going to choose in some way. And as this shows, she sent over commit. At that point, Vic also knows Y, since it's just X times commit inverse. And then she makes two claims. She claims that both commit and Y are quadratic residues. Now, if she's able to prove those claims, then by our prior arguments, she's done, because we saw that if both those are true, then big X has to be a quadratic residue. However, the trick to make it zero-knowledge is that Vic isn't going to check both these claims. He's going to pick one at random and ask Peggy to prove it. So he's going to say, okay, you're making two claims that commit is a square and Y is a square. I'm going to spot check that. I'm going to say, pick one of the claims, 0 or 1 at random, and now prove me that one. Peggy delivers the proof in the obvious way, actually. She just sends a square root of whichever object is requested. If Vic says prove this is a square, she sends its square root. If he says prove this is a square, she sends the square root of that. Of course, we'll have to set things up so that she has these values. But the neat thing about this is that you get the kind of properties we want. If you first start by considering soundness, you see that if x was not a square, by the prior slide, one of these claims is false. So that means that when Vic makes a random choice, with probably half he'll pick the one that's false. And then Peggy is stuck. There's just nothing she can do to reveal a square root. So probably half cheating will be caught. But on the other hand, if the claim is true, we see that no information about little x is revealed because effectively both these components are independent of big X taken individually. And it's a little paradoxical that something like that is possible, but we'll see how that works out. Okay, so now we come to the actual protocol. So what Peggy does is she picks a point in Z and star at random, call it C, and she creates a commitment by squaring that mod n. And that's what she sends over. Now notice that she knows a square root of this, which is just little c, and also notice that it's a random quadratic residue. At this point, Vic gets this, and it's quite meaningless in the sense it has no relationship to n or x, so he learns nothing from this. But nonetheless, at this point, the implicit claims that we wanted to think about earlier have been made. In other words, at this point, Peggy is implicitly saying, I'm claiming this is a square, and I'm claiming that x times this inverse, which we call y, is a square. So Vic now is saying, I'm asking you to establish one of those two claims. And she can do that. How does she do that? Well, she needs to send a square root of this if he picked that claim, and a square root of x times this inverse, which is y, if he picked the other claim. You can encapsulate those into one equation. So look at the quantity commit inverse times x to the power the challenge. If the challenge is 0, that's just commit inverse. If the challenge is 1, it's commit inverse times x. So those are the two quantities in the claim, the two that we want to check are squares. Vic is picking one of them at random by sending this. And what Peggy does is she constructs this object. This thing here, inverted, times little x. What is little x? It's the square root of big X that she has as a private input raised to the power of the challenge. Now here she's using little x. So we would be worried that information about it is getting revealed. But she's also multiplying it by some sort of random other thing. And that's what will ensure that it isn't actually revealed. Vic can check this. He squares this object and sees that he gets back this here. And this convinces him that this object here is a square, and that's it. That's what he wants to be convinced about. So we can go through the different properties. So again, we start with completeness. So suppose that big X was indeed a square mod n, and Peggy is honest. Will Vic accept or will he not? He does, and that's just pure algebra. We need to check that this D here will be true. Well, let's just see. Take this response squared, but now we know response is computed like this. So the square of it is C inverse times x to the challenge squared. So let's expand that. We can move the square into here and take the inverse outside. And similarly here, we move the square in and take the raising to the ch outside. But we know that the square of little c is the commitment. So here we get commit inverse. We know that little x squared is big X. That was the entire assumption. So we get this, which is what's here. What about soundness? Here we must replace Peggy with a potentially cheating prover. We now know that big N and big X, the pair, is not in the language of quadratic residues. This thing does not have any square roots mod n. Nonetheless, Peggy is claiming that big X is a square. She will now create commitment, not in the way we saw earlier, but in any way she wants, with the hope that she can later create a response, again doing whatever she wants, such that this equation becomes true. So her goal is to make this equation true. Our argument is that no matter what she sends here and here, the fact that this is random means that only half the time will she succeed in making the equation true. And that needs a little bit of argument. So for notational sake, let's define big Y to be commit inverse times X, so that big X can be written, thought of as commit times Y as per our previous splitting intuition. Now we know by assumption that big X is not a quadratic residue. So then the fact we saw earlier tells us that one of commit or big Y also must fail. It can't be a quadratic residue. But this is why Peggy is stuck. What happens is at the point that this has been sent, if you look at this object here, either for challenge equals 0 or challenge equals 1, this object is simply not a quadratic residue. And if that happens, she has no choice to make here that will convince Vic. So she would be stuck over there. Okay, and we come now to the final property. What can we say about zero knowledge? We want to say that that Peggy doesn't actually reveal her secret little x. The verifier doesn't learn anything. So we look at what she sends. She sends this object over here, and indeed it does depend on little x. But our claim is that it's kind of a random square root of this object. And due to the fact that this object is multiplying big X by something, is not actually going to reveal a square root of big X. Okay, so however, that was pretty vague. So the zero knowledge part, in the sense that we haven't actually said what zero knowledge even means to the point that we can argue that the protocol has that property. So we want to next move on to doing that.